Morning. Please do come in and get yourself seated. We like to give the Shannon Lecture all possible time to tell us what he's going to tell us. I had a chance yesterday to say as much as I'm going to say about our Shannon Lecturer, Robert M. Gray of Stanford University. So today all I'll do is say, Bob, I'm just delighted that you're the Shannon Lecturer, and we're looking forward to hearing your talk.
Thank you, Dave. Being horribly absent-minded and getting worse at that, I would like to start at the end and say the really important stuff first, so I don't end up getting rushed through that. I don't mind cutting myself off with the technical stuff, but thanking people and acknowledging and maybe a few stories about how I became an information theorist merits a little bit of time. So I'll add on to my thanks yesterday to the Society. Perhaps I can just not be redundant, take advantage of the fact that Canada is bilingual and say, je voudrais vous remercier extrêmement fort parce que je suis très honoré par cet honneur que vous m'avez donné. Alors, I'll go back to English because it's safer. But thank you all. Thanks to the Society. Rob used my line, but I'll repeat it. I'd like to thank my sponsors, the National Science Foundation, that has funded me since I was a student, Hewlett-Packard, whose generous gifts over the past couple of decades have allowed my students and me to travel, attend conferences, have good computers. I'd like to acknowledge both of them. That's my dissertation committee. Erwin Jacobs was both my master's thesis advisor and on my PhD committee, although he was at a different university. Bob Schultz in the middle and Lloyd Welch, a previous Shannon winner, on the right. They're the ones who really taught me advanced information theory and got me interested in research and an academic career, and I owe them an enormous debt of thanks. I'd like to repeat my thanking of colleagues and former students, but with a little bit more detail, and I'm not going to name everybody, but I thought I would show photos of my co-authors, mostly students, but not all former students, highlight a couple of them to make some remarks, and they're in roughly inverse chronological order according to when the last or the most recent paper I wrote with them. The upper left is Tomasz Linder, whom I would like to particularly thank. Not only has he been a recent collaborator and co-author, he looked at several early versions of these slides. Richard Olshan on the far right has been a co-author, collaborator, and friend for many, many years. You see Dave Newhoff on the second line. He was actually my third PhD student, but he's up at the front because of the fairly recent tutorial that we wrote. The bottom right I show because if you've never supervised a pair of identical twins, you can't imagine some of the fascinating issues that crop up. They got virtually identical grades through their entire career, identical scores on their qualifying exams, but they had to really bifurcate for PhD theses, and that was an fascinating exercise. Alan Gershow on the top left has been a longtime collaborator. We wrote a book together of the books I've written, which Dave Forney mentioned yesterday. That's the one that seems to have actually sold well enough to allow me to have some very nice dinners on royalties. Far top right and left on the middle, Phil Chow and Tom Lookabout. That was some of the more fun collaborative research that I did. I learned a lot from them. In the middle of that row is Lee Davison on La Boheme. He apologizes for not being here. He's somewhere in the South Pacific, not too far from Java. Can't understand why I'd rather be there than here. Bottom next to the left is Tom Stockham. I'd like to single him out. He was a mentor of mine, a friend of mine. When I was young, he took me to dinners fairly regularly to talk about career, life, and quantization. Like Shannon, he had Alzheimer's. Unlike Shannon, he had it before he was 60 years old. It was early onset. Alzheimer's is tragic. It's doubly tragic when it hits somebody that young, a point I'll make again later. And I think the tragedy is as great for us who miss him and lose him as it is for the victim. But thanks, Tom. Mari Ostendorf in the top, second from the right. About a third of my PhD students have been women. She was the first, and in fact, after she started, about a half of my PhD students have been women. And she started in the early 80s when the atmosphere in EE was, I would say, almost actively hostile towards women. Not that she complained about this. She was remarkable at putting up with many indignities and problems. But she served as a magnet for the future, which provided me some of my absolute best students. And I also found out a lot about the field and have since been trying to actively work to improve those situations for all people who find an uncomfortable atmosphere in the field. Bottom left, the circled gentleman is Mike Pursley with Claude Shannon on the far left. This is at Ashkelon. I'll say a few more words about that later. The next picture is my oldest brother, Steen, and John Markle, with whom I spent many years doing speech research. I like the picture showing the haircuts and the computers of that vintage, late 70s. The two gentlemen on the far right are Buzo on the far right and Josef Linde. One young, one old photo. It's what I found on the web. Linde makes the point, if you are an information theorist and want to become rich, one way to do it is to become a venture capitalist. He has done very well, nothing to do with information theory. The gentleman, the second from the right, is Don Orenstein. You might describe him as the Shannon of ergodic theory. Much of my talk will be related to things that he did. Paul Shields on the far right, I apprenticed to him for about 2 years to learn ergodic theory so I could understand what Orenstein was talking about, that it was not easily approached. I guess on the bottom line, the two gentlemen on the left were my first two students, Bill Perlman, who's been very successful in image processing, Barry Leiner, who was lost quite young to Lou Gehrig's disease. Bob Towsworth is the terrible picture. It's all I could find. He was my supervisor at JPL. When I showed up as an intern, I met the likes of Saul Galam and Andy Viterbi and Chuck Greenhall and Bill Lindsay and Ed Posner and Gus Solomon. And that was a fascinating time of my life. I might have stayed if it hadn't been for the smog in Pasadena and the fact you could look out these gorgeous windows and not see the mountains across the street. I understand it's better, but then it was pretty awful. Okay, I may sound a little bit morbid, having dwelled on some of the former students who have passed. I'd like to, I guess, make a comment that perhaps one bottom line of this talk, which I'll repeat in a moment, is that this teaches me that I should enjoy all the health I've got and have as much fun as I can and not sweat the nickel and dime stuff about the aches and pains of growing older. There's an even stronger reason for my giving this advice, which has nothing to do with the technical part of the talk. Okay, I'd like to thank my family. The upper left is to show everybody who's never seen me without a beard what I looked like. I'm the one on the right in high school. You have to be getting on to have seen me without a beard, since I've had it since 1966. But that shows my 4 sibs and parents, my immediate family in Japan in the early 80s, my wife Lolly, son Tim, daughter Lori. I would like to thank them from the bottom of my heart for everything. I would not be here without them. The whole clan in my great-great-great-grandfather's house in Ipswich, Massachusetts in the mid-80s. And then at the Fort Rosecrans Cemetery, following the memorial for my mother, is essentially the same crowd. Being an amateur historian, I'm rather fond of visiting cemeteries. I go to them whenever I can, look up famous people, find out about them. I have to admit that this is the most beautiful one I've ever seen. My father said he bought the plot because he really liked the view. This is the immediate family at the mentoring award that Dave mentioned, which was another very proud time for me. And they were a bit older and I'm a bit grayer. And on the bottom left, you see the kids of my son Tim, and on the bottom right, the kids of my daughter Lori. So to my family, I extend a great thanks and acknowledgement. And I'd like to dedicate this talk to my next older brother, Pete. He was famous at MIT as being, so far as I know, the only MIT PhD student to successfully complete a dissertation under Bill Siebert. He was also famous as a world-class sailor. He was the last skipper to win for MIT the North American Dinghy Sailing Championships. He was probably more active in the signal processing area, but like Tom Stockham, he was cut down around the age of 60 by Alzheimer's. And so I'll simply reiterate the point that I made before. Don't sweat the nickel and dime stuff. Be grateful for the health that you've got and enjoy it to the fullest. And I really wish that he were here to see this talk today. Okay, how did I become an information theorist? My friends, many of them, can brag they knew Shannon, worked with him, talked to him. I didn't meet him until Eshkelon, but I did know about his work earlier than many of my colleagues. As a junior high student in 1957, I got one of these machines, arguably one of the first personal computers sold through the magazines. These are the ads I may have seen at the time. I pulled those from Scientific American. These were made by a guy named Edmund Berkeley, and Betty Shannon told me the story after the installation of the Shannon statue in Gladstone, that Berkeley would bug Shannon. He would come to their house all the time. She wanted to throw him out and lock the door, but Shannon, being very kind, let him come in and bore him for hours and help him put together the booklet of 400 experiments that you could do with this machine of spinning dials and wires. With the machine came this paper, which you've already heard about. This was Shannon's master's thesis. He's a student member here. This is the original copy, which I still had. And I hardly understood a word, being in junior high, but I did catch the bit in the center about binary arithmetic, that you could do arithmetic with zeros and ones, and that later led to a high school science fair project. This is the course that Dave Forney mentioned, Information Theory, 6574. This was in September of 1964. It started, taught by Bob Gallagher. And when I first told Dave about this, he didn't really believe he'd been a TA. And I think that was because he was kind of an informal TA as a favor to his professor. And I just wanted to show this page to prove it, that he was the person who ran the grading sessions, and I still have a memory of him. Unlike most of our coat and tie TAs standing at the board, he was sitting on the table looking quite comfortable and gesticulating as he went through the homework problems. This is the main memory I have from that class. I know you probably can't read it, but it's out of Gallagher's book where he says, this problem is due to the author and it was used as a take-home exam. Mine was the class that got it. He handed it out just before Christmas vacation. Everybody in the class canceled their Christmas vacation, spent the entire time working on this problem. Everybody got above 95 on it. So it didn't count at all. But we all got overconfident. I blew the final. I got a B+ in information theory. So that's to encourage people when, don't worry about it if you don't get right off the bat with it. Keep to it, and eventually it may work out. And in fact, the next summer, I found that this was not all theory. I was a 6A, a co-op student at MIT. I went off to the Naval Ordnance Lab. I was given this project to analyze, which was a communications link between an underwater sensor and an airplane trying to track submarines. And they had a data rate they wanted to send at and a bit error rate that they required. And I realized the data rate was something like 10 times, or pardon me, channel capacity was something like 1/10 of the data rate that they wanted to send at. And they wanted an arbitrarily small probability of error. So I said, actually, this is impossible. And they said, well, no, it isn't, because they'd already given out a very large contract to somebody to build this thing. So I learned a lot technically, also politically. I was quickly transferred and put to work on countermeasures, and I have no idea what happened to the rest of it. The next step is when I went to USC, I spent an afternoon talking with Erwin Jacobs, trying to find a thesis topic, and he said, Shannon wrote this great paper, and hardly anybody's looked at this stuff since. And so it's perfect for somebody young looking for a PhD. It's in source coding. Nowadays, I think we think about information theory as channel coding and source coding, and channel coding's bigger, but source coding is not negligible. Then it was negligible. There were maybe fewer than 10 people really working at it. This is the copy, heavily annotated, of the paper that he gave me. To sort of wrap up this part, leaping ahead to 1973, the other Shannon brag that I have is people may have been friends, written papers with him, and known him, but he came to my wedding reception. That my wife and I were married the week before Eshkelon, secretly because everybody thought we already were. But a couple of friends knew about the marriage, one of them being Lee Davison there on the left, and they organized this wedding reception, which was very nice, except they organized it for after the banquet. Now, that banquet, and I hope I don't insult anybody, probably had the most deadly banquet speaker in all of history. And they had warm martinis and no wine. So everybody by the end was thoroughly bored, exhausted, and probably more than a little tipsy, which meant everybody wanted to go to bed when suddenly we were grabbed, whisked off to this room, the doors flew open, and surprise, and there was this party. Lee and friends had found the only 3 bottles of champagne within a 30-mile radius of Eshkelon. And Shannon was there, as you can see, with a glass of wine in his hand. And Lee is holding a vase, which we still have, which was our wedding present. And you see a young Dave Forney there as well, and Pina Longo and his wife. That reception went on quite a while, and then it felt like crack of dawn. Early the next morning, Shannon had to give the Shannon Lecture. Well, I think both the lecturer and the audience were a little bit worse for the wear after that. And so I'd also like to thank the Society for not having this lecture the morning after the banquet, which is a great idea. Okay, so let me now actually try and say something technical. And what I'd like to talk about is this. And the basic idea is really in this slide, and the talk's going to be picking it apart and making some observations, mostly old, a few new. The top is a source coding system, taking a source, putting it into an encoder, mapping it into bits, then unmapping it through a decoder to get a reproduction. The bottom is a simulation or synthesis or fake process. All of those words have been used for this. And it takes simply a collection of random bits, and I'll say more about what I mean by that, but you can guess, maybe coin flips. It puts it through a coder, and out comes a fake version of some process. And what I mean by that is you have a process model, and you'd like something that has more or less the same distributions, or if you can't do that, as close as you can possibly get, so you have to worry about what close means. This problem actually first arose in dealing with trellis encoding for source coding, because you wanted to have a fake version of the process that you could somehow generate by a finite state machine or a filter to color a trellis and then search it. So one way to populate that was to put just bits, that is what you would get out of receiving a sequence of bits, into some kind of a coder that would either give you one label or another depending on what happened. But right now I'll just take it in the abstract. So just from the way I've drawn the picture, you can see these two things are related, and that's what the talk is about. Okay, for a source, I'm going to take a stationary and ergodic source, and I'll point out that I don't think this is as narrow as sometimes it is impugned. That if it's not ergodic, then a little math shows you it is a mixture of stationary ergodic sources. If it's not stationary, but it has converging relative frequencies, then it has some form of asymptotic stationarity property. All of those just make everything more difficult, but most of the stuff remains the same. So everything I say will be about stationary and ergodic processes. I will allow continuous things like recorded analog speech or images, discrete things. I'll talk about differences as I go along. A little bit of notation as I'll need to use vectors. Shannon entropy, I will write out just to make sure everybody understands what I mean. I define the entropy of a vector as that sum of probability log probability if things are discrete, and infinite otherwise. I am not talking about differential entropy. While I don't feel as negatively about it as Sergio does, it doesn't have a role here. So a continuous process has infinite entropy. The Shannon entropy rate, often I'll drop the word rate, means simply taking a limit or an infimum. They're the same thing because we're dealing with stationary stuff. I'm not going to define the other measures like mutual information, but I will use them. Okay, here's the source coding with a fidelity criterion. Shannon, 1959, laid this down, as you've heard lots of times before, in remarkably complete form. And basic ideas, we'll take the source, same picture you saw before, put it into a coder, out come bits. And the issue is, the more bits I give you, the better quality or reproduction you can get. What is the optimal trade-off? If I constrain the bit rate, how small can I get the distortion, for example? This leads to several things: Shannon rate distortion theory, source coding with a fidelity criteria, lossy data compression, and quantization. And I tend to mean by quantization vector quantization. That is going from continuous to discrete, whether it's vectors or scalars. The simulation problem, which is much younger, as I put its origins in 1977, is the random bits problem, going in and trying to make a simulated version of a process. Think, for example, you've got a process here, you want to describe the parameters to somebody there, and then they're going to simulate their own version of it. So they're not going to try and match waveforms. They're going to try and produce a process that has the same description. So I'd like to know what the best simulation is, and I'm going to put some constraints. I would like to have simple random bit generation, for example, coin flips. I'm going to require a stationary or time-invariant coder. I'll say more about that later. But the main reason is, if that coder is stationary or time-invariant, then because my input is stationary and ergodic, so is the output. My input is mixing, so is the output. If it's got certain other statistical properties, then the fake will inherit those properties. And then I'm going to put a constraint of the number of bits. I'll also be curious about what if that constraint is infinite. So I'd like the simulated process to inherit properties, as I've just said. One of the properties, maybe not as familiar, has a variety of names, sometimes called the 0-1 law, sometimes said to be purely non-deterministic. If you deal with continuous Gaussian processes, this is the integral of the log of the spectral density is not minus infinity. It's called a Kolmogorov or K-automorphism in ergodic theory, but it is even a tighter constraint than mixing, but a class of random processes of interest to a lot of people. We'd like it to resemble the original process as closely as possible. I have to specify what that means. And it would be nice if I give you infinite bits, you can have a perfect recreation of the process. Get the distributions right exactly. And what I'll warn you in advance is ergodic theorists know that's not impossible. If I try and do it by taking a stationary, that is not possible. If I try and do it by having a stationary mapping of IID stuff. So part of my talk is actually about modeling. That's a nice kind of model, but exactly how general is it? And that's one of the questions. Okay, I should here mention the work of Steinberg and Verdu. It is intimately related, but Sergio and I haven't really had time to sit down and figure out how intimately related it is. It also uses the name the simulation problem, which goes back to the 70s. It also worries about optimal simulation and relating it to source coding, but the requirements for what optimal simulation means are different. He doesn't require stationary and ergodic. The results are more general. And I'll say a few more words about it later, about the parts I do understand. But those results suggest some of the things I talk about may be more general, but it's not clear if they are or not. Okay, this is the anchor of my talk, the common thread, and it is an information theoretic folk theorem. One thing that occurred to me is, how do I prove to you that something's a folk theorem? Okay, we don't have books on folk theorems in information theory. Okay, I went out and I asked 6 information theorists. 4 agreed this is what they believed. 1 looked at me puzzled and said, what? The other said, bits. Oh, you mean indexes. Okay, so I will try and say words to accommodate that, but I'll just say this is something I always thought was true and lots of people I talked with. And the claim is, if you've got a source coding system and from input to output is really close to what Shannon says you can do in the limit, then the bits you're sending in the middle ought to be very close to coin flips, very close to IID equal probable. Now, in a sense, that's intuitive because that says they're carrying the maximum amount of information that you possibly can when you're sending bits. Now, one of the cases I will focus on, just because it's simpler, is what happens when you send one bit for every symbol. Things get a little more complicated when you're doing something else. So here the claim is if you're sending Gaussian from here to there and it's really close to the Shannon limit, then those bits should look like coin flips. All right, is that true? Well, one point is this provides the obvious connection between the two problems. Because I said I wanted to simulate by IID, so if you've got IID in the middle of a source coding system, well, then the two problems are related. The bits in the middle seem to pretty much be the same kind of thing. That maybe they're not exactly IID, but if they're close to IID, and if in the source coding problem I can drive a decoder and get the best possible Shannon-style reproduction, well then that, maybe I just can't do any better if I'm trying to simulate. Conversely, if I can do a really great job of simulating with a stationary code, then I can use that stationary code, which is really just a sliding block code, a shift register and a nonlinear possibly operation, color a trellis, search it with Viterbi, impractical maybe, but it should give you a good compression system. So here are the three questions for today. Does nearly optimal performance imply nearly IID bits? And then are source decoders, source and simulators equivalent, as I've sort of waved hands? And is source coding and simulation problems equivalent? All right, the answer to the second two questions is under certain constraints, yes, and that's an old answer. And the new bit for today is really the first question. All right, there are two kinds of codings that we deal with. One is block coding. That's what almost all information theorists do. You take a block, you map it into a block, you forget everything you've done, you look at the next block, and you map it into a block of stuff. The other kind is sliding block coding, where you take a block, or a window it's often called, and you produce one bit, say. Then you slide the window over, perform the same operation, and you produce the next bit. Okay, this is going to make a critical difference which kind of code I'm talking about, and I'll simply mention that the information theory and ergodic theory literature dealt with constructing one kind of code from the other a lot during the 1970s. Paul Shields has a very nice book which goes through all of these constructions. And I've already said a couple of words about that in my discussion of trellis, but suffice it to say you can pretty much go from one to the other, so the source coding results I'll mention really should not come as a surprise. This is just a graphic to point out what I just described. Martin Morf once described it as a block code. You're driving a car on a really rocky road. You look ahead 100 yards, plan a path, close your eyes, you drive it, and then you look ahead and do the next. If it's a sliding block code, you look ahead 100 yards and just drive the next foot, having seen the context that it's in, and then you look ahead again. So it's much more incremental in nature. Okay, block coding. Well, it's the 800-pound gorilla. A lot more is known about how you design these codes, and source coding and channel coding. Transform codes, vector quantization, clustering algorithms, most codes that are dealt with in theory in the real life. But you lose all the statistical properties of the original process. I mean, just go to any book, well, go to Bob Gallagher's book, for example, and see how difficult the proof of the general coding theorem is once you get away from IID. Instead of getting stationary, you get block stationary. Even if the original source is ergodic, it may not be block ergodic when you come out. So you lose lots of stuff that basically says, for example, if you use a block code for simulation, you won't inherit the properties that you want of the original process. Okay, one other problem is in block coding, a lot of theorems say is codes get bigger, things get better, but there's no notion of a code in the limit. There is no code at infinite length towards which you are going, all right? Doesn't make sense. You would start the block at the beginning of the universe, end it at the end of universe, and that's it. There's no dynamic motion. There's no time involved. Sliding block coding, perfectly well defined if you've got an infinite window. And in fact, in practical systems, you do effectively have an infinite window. Anything with feedback is going to depend on the infinite past in some way. And so something like a delta modulator or predictive quantizer is a sliding block code. Now, I should also mention, in fairness, because this is a natural question, even though you've lost these stationarity properties, you could throw in a random phase to start this thing and get a stationary process. But block coding can result in certain periodic structures. You can actually look at the sequence and figure out where things start. And that still happens even if you randomize the start. It doesn't get you back ergodicity, and it doesn't have an equivalent operation as a sliding block or stationary operation on your original process. Okay, sliding block preserves the properties. It's well-defined, as I mentioned. It models several signal processing and coding algorithms. One thing I like to point out is when you build convolutional codes, all right, they're essentially a sliding block operation. They're a linear filtering. Most of the theorems for convolutional codes involve time-varying convolutional codes, which is not the way they're usually built. A time-invariant convolutional code is an example of a sliding block code, at least the convolutional part. Then when you do the search part on the other side, depending on whether it's channel or source coding, then that tends to be a block operation. But the real reason sliding block codes came about was because of their importance in ergodic theory, and that brings me to the Kolmogorov-Sinai-Orenstein isomorphism theorem. So here's my attempt at a very simple explanation of that theorem. The picture at the top is a graphical representation of a sliding block code where you can imagine it goes on forever, okay? So you look at it, you print out one thing, then you slide it and you print out the next thing. Now, two random processes are isomorphic if I can code one using a sliding block encoder into the other in an invertible way. It's like an infinite length lossless code. And that's the same definition whether things are discrete or continuous. I can go from here to there and back again with a stationary mapping. All right, one side thing I need to make the next statement is there is a class of processes named by Don Orenstein. There are lots of names for it, lots of equivalent definitions for it. I'll take the simplest, which is a B process is a stationary coding of an IID process. All right, if that sounds familiar, it's on purpose. But that says anything you can take coin flips, roulette wheels, IID Gaussian, stick it into a sliding block code, maybe I'll call it a filter if the output is continuous, that's a B process. All right, Orenstein proved that if you have two B processes, they will be isomorphic, you can go into one and back, if and only if they have the same entropy. Okay, that's it. The Orenstein theorem, sometimes called Sinai-Kolmogorov, because they prove necessity. Orenstein proves sufficiency. And you can see that sliding block codes are just inherent in the definition. Okay, a few more words about source coding. To define optimal source codes, I need the notion of a distortion measure. I need a decoder, which is going to decode my binary blocks or indexes into reproductions. I need an encoder that looks at blocks of input and prints out that binary vector or index. I look at the average distortion. I look at an average rate. I've stuck in both forms, the so-called fixed rate codes and the variable rate codes. One is going to constrain just the number of code words, the other the entropy. I'm going to focus on fixed rate for simplicity. The entropy enters in a natural way, and similar things hold if I use the variable rate. What is the optimal performance? Well, just look at your block and find the encoder and decoder that give you the minimum average distortion subject to a constrained rate. That's the operational distortion rate function for a block length n code. The overall optimal, we'll just take the smallest possible overall block sizes, and that proves to be simply a limit. Not computable, Shannon saved the day. The Shannon rate distortion, or distortion rate function I'll deal with, the dual, is defined below, and it's also usually defined in terms of a block optimization, where now you minimize distortion, but not over codes. You do it over measures on the input and output, where the input agrees with your source and the joint measure has a constrained mutual information. And the famous source coding theorem basically says the operational and the Shannon distortion rate function are the same. Sliding block codes play the same game. Look at finite order, and then take the infimum or minimum over all possible sizes, constraint lengths of those codes. Here we get the benefit that we can actually write it down more simply, is simply take the minimum or infimum over all possible sliding block codes, infinite length or finite length. And here the source coding theorem says, unsurprisingly, that the operational distortion rate, the optimal performance for block and sliding block is the same. Okay, just a reminder, if you build encoder, decoder, reproduction, the top shows what blocks are doing, the bottom shows what sliding blocks, and this allows me to just remind you of one of my fundamental questions, which we now have to get a little closer to, is if things overall are near Shannon, are those U's, those bits in between, nearly coin flips? Do they look nearly IID? How do I pin down, quantify the notion of nearly IID? Well, one way is to use the idea of a process distortion measure, and we'll see this also gives us a way of pinning down what I mean by an optimal simulation. The process distortion measure that I'm going to deal with is given many names. I think the three most important are Kantorovich. He got the Nobel Prize partially because he developed linear programming. He was one of, I think, the three people honored for that. And linear programming was intimately connected with this distortion measure. I mention that simply because this distortion measure ends up getting rediscovered about a decade ago in the computer science field. And surprise, you could use linear programming to evaluate it. Okay, well, that goes back to its origin. Wasserstein is the way I discovered it, and I think the way it first came into information theory. And then Orenstein made it an essential part of modern ergodic theory when he revolutionized it and solved the major problems there. And he really did some stuff that was different. So, whoops. Let me tell you the basic idea. If you have a distortion measure and you've got two random processes, step one, look at vectors, random vectors. Look at any joint probability distribution on those vectors that agrees with the distributions you started with for the marginals. But find the one that minimizes the average distortion between the two. So it's a matching distortion measure, cropped up in something called the transportation problem first, where you're sort of moving stuff around, keeping the marginals fixed, and trying to get some match between the two minimized. And then you define the measure for processes by simply taking the maximum, the supremum, overall vector sizes n. And it turns out that you can actually just define the distortion measure as an infimum over all processes that agree with the two marginal processes. Okay, one of the definitions, by the way, is if things are stationary and ergodic, take a typical sequence of one. How much do you have to tweak it to get a typical sequence of the other? And the tweaking degree is measured by your distortion measure, which might be Hamming for discrete, squared error otherwise. Okay, just the historical side, this goes back to 1942 at least. It was looked at by a lot of people for scalar distortion measures. That was what was used almost entirely until Orenstein in the early 70s explicitly worked on vectors, used the Hamming distance. Kantorovich and others had used L1 and L2, LP more generally. And he looked not only at vectors, but he looked at processes. And so far as I know, he did it first for processes. So I'll use his name, which is D bar, when talking about discrete. And here, being a little bit egotistical, Dave Newhoff, Paul Shields, and I, knowing about Orenstein and Wasserstein, but not all of the others, took his idea and adopted it for squared error type distortion. We call it rho bar after D bar. And that's easier to say than LP minimal metric, which is now used because after the rho bar stuff, people started applying Kantorovich to vectors, and the connection between the two is there. So if I say D bar, think discrete, Hamming match. If I say rho bar, think continuous, squared error match. Okay, the snide comment at the bottom is this was rediscovered in the CS community called the Earth movers distance, used in pattern recognition. Then somebody discovered that, oh, gee, this has been around for a while, and changed the name to the Mallows distance, who in '72 rediscovered the Kantorovich scalar case without knowing about it. So this was a bit of a case of myopia, I think, but lots of definitions for it. Okay, just a few properties. These things are metrics. If your original distortion measure is either an LP metric or if take the LP metric, take it to the P, take your average, and then take 1 over P. So it's the rho bar to the 1 over R if it's an LR metric. The infimum is actually a minimum. That means the joint probability when you're doing it, that it actually exists, that has those prescribed marginals. That's a big area in itself. One of the things I most like is it says that if you're talking about discrete alphabet B processes, it's exactly the same as the collection of all kth order mixing Markov sources and the limits of those things in the d-bar distance. So it's everything you can approximate by a well-behaved Markov source. The entropy rate is continuous in d-bar. If d-bar goes down, then the entropy rates become the same. That was critical to ergodic theory. The Shannon distortion rate function is continuous in rho bar. In d-bar, if you're talking discrete and Hamming distance. You can evaluate these for IID processes, for general Gaussian, for general uniform IID put through filters for a lot of cases, and in general, it's linear programming. Okay, first application. It gives you a geometric view of the distortion rate function. If I want the distortion rate function of this source, then what I do is I look at all possible sources that have an entropy rate less than R and find the one that's the best rho bar fit. So I find the nearest neighbor process with my rate constraint. So that's the definition on top. Now that's almost a simulation because that tells you we can go find a fake of the original process that's got a constrained bit rate. But it doesn't fit what I wanted before because there's no simple IID generation to it. All right, this could be a stationary and ergodic process, but it's not necessarily going to be a B process and obtainable by stationary coding of IID. Now, at the bottom I mentioned that this idea of defining these things in terms of processes, you can also do a straight Shannon version of that, where you take the source, look at joint measures giving you the source, and minimize with them mutual information rates that are constrained. And this gives you the same thing. Quantization is distribution approximation. Pollard and then Graf and Luchy knew about the rho bar stuff and realized that any quantizer, vector quantizer, is really equivalent to a model of a discrete source in vector space. Well, that gives you a simulator. What you do is each block, you IID according to this marginal, according to this probability on the set of possible code words, generate those code words, and then just repeat it into the future. And what that gives you is a process that is rho bar on a block basis close to the original. But unfortunately, you can't get a nice process result about that. And if you generate these things independently, you get something that's block stationary, but it is not stationary, and you cannot construct a stationary mapping of IID to get the simulation. So this is sort of a simulation, but not quite. All right, here's the old optimal simulation using now the process distance. I want to simulate X. I've got an IID process Z. What's the optimal simulation? Well, I'd say it's fairly natural. Take your IID, look at all possible sliding block codings of that IID process, and then find the one that is closest to the source in your rho bar distance. So it's essentially a find the nearest neighbor subject to the fact that it's an IID process into a filter or code. That sliding block code, by the way, can have infinite length, but there's a basic theorem that tells you any sliding block code with infinite length can be approximated as close as you'd like in its performance by one with finite length. Okay, since sliding block coding reduces entropy, that capital delta function has to be bound below by the smallest possible distance you could get between any stationary and ergodic process, B or not. But that we've already seen is just the Shannon rate distortion function. So delta gives me an upper bound on Shannon. And again, kind of an intuition of this is simulate the process, color a trellis, do a search. You can get a source code with roughly that distortion. That's got to be worse than the distortion rate function. But if X is a B process, that is, if X itself is something like a Gaussian autoregressive, purely non-deterministic process, then you get the other way as well. And without going into details, the essential part of that is if I've got a sliding block coding to get my process, then going to these U by a sliding block coding is I have overall a sliding block coding and I can just optimize over that. So the picture basically is showing that if you can get UN to be a B process, an ergodic theorem, theorem from ergodic theory tells you I can code that from an IID process. So that gives me a simulation, so it can't be any better than the optimal simulation. So this is an old result basically saying for B processes, the two problems are equivalent, and actually you can show that decoders for source coding are the same as simulators. What about the bit problem? Okay, once again, if things are near Shannon, do I get nearly uniform IID bits? Okay, what if I have a block code? Shannon tells me I can construct a sequence of block codes that get close to the distortion rate function. So I can write down a series of inequalities, which will simply say, if I've got, say, 1 bit per symbol, 1 is bigger than, well, is the same thing as simply taking 1 over n log the code size. That's bigger than the entropy of the encoded, and then a simple sequence of inequalities gives me a lower bound that goes to 1. All right, that's interesting because it says the nth order entropy, as those codes grow, is actually going to its maximum possible value. So in a sense, those things are as uniform as they could possibly be. All righty. Is that enough? No, because it doesn't give me a process result, and it doesn't give me an entropy rate, because entropy rate sits below block entropy, so I can never be sure that that is going to be going up to 1. If it's a sliding block coding, though, the same little sequence of inequalities gives me a sequence of processes, which I can prove actually have an entropy rate going to 1, and then using a result of Cathy-Martin's, which this proof came out of a conversation with Tomasz Linder, so I give him credit for finding the simple proof. That means that the d bar distance between my encoded process is converging in d bar to 1 if I've got a binary source. And that means that binary source has to be IID coin flips. Because if you get arbitrarily close to IID coin flips, in the limit you have to be going to IID coin flips. So this actually solves that folk theorem for a particular type of simulator, that if the average distortion gets near the Shannon limit, then you're in good shape. It's actually going to be IID, provably IID and d bar. Okay, sort of a recap of results before some observations and final comments. The old results is if we're considering stationary filtering and you're performing near the Shannon optimal and you're considering B processes, then source coding and simulation are equivalent. One problem gives you the other. The source decoder is the same as the simulator. So that means if you want to look at the problem of optimum simulator design, as a side benefit, you can get optimal source codes. The new result is that B process or not, if it's stationary and ergodic and you have stationary codes, if your performance is going to Shannon, then those bits must be going to a coin flips, IID binary. Okay, the frosting, by that I just mean that looking at these problems is really just a thinly disguised excuse for me to talk about issues that I like, which are common to ergodic theory and information theory. There are a few of us in information theory who have spent a lot of time in both, and the intersection is a lot of fun. So some final thoughts and questions. D bar close to an IID, is that actually good for anything? It's nice for intuition, proves a folk theorem, but B processes have all these wonderful properties. There are books written about them. Do almost B processes that are D bar close have similar properties? Don't know. Be nice to look at. Does the equivalence that I've proved you hold as generally as the results of Sergio et al. Hold? Well, on one hand, you'd sort of suspect, because the problems are close, and his work for stationary and ergodic as well as more generally than that. But there's a danger here because the ergodic theorists know that B processes don't give you everything. Okay, source coding is an almost isomorphism. It gets away from the hard part of isomorphism. You don't deal with the invertibility. So that's maybe of interest to the mathematicians. I don't know. There's some interesting connections with Itakura-Saito distortion, which is used implicitly in speech processing. It would be fun to look at that. B processes have a shortcoming as models because, for example, if you use them in speech, you only get whispered speech, unvoiced sounds. To get voice sounds, you need to have inputs that are not IID, but are periodic. That is, they have zero entropy. So what happens with all of this when you have processes that can, say, switch between zero entropy and B processes? Pinsker had a famous conjecture that sort of said something like that should get you all processes. Orenstein proved that was false. And then how do you actually design simulators? And I won't actually go through some hand waving on that, but I think there's some interesting ways to try and get Gaussian out of bits. What I would like to do is sort of end returning to the introduction and see if it works and tell you why really I became an information theorist. Because at this point, many of my predecessors broke into song. And I think maybe the volume can go up just a little bit so you can be glad that I became an information theorist and not a famous rock musician. That's me on the right, in case you can't tell. And so with that, I'd like to thank you very much, and you can kill the music, and I'd be happy to take any questions. That's all right.
Who has the second question?
I need Dave Newhoff here, and unfortunately, he had a family emergency, and so he's not to serve as my shill in the audience. But Tony promised to heckle me. Well, there are actually a couple of things. First, he thanked me for putting my textbooks online. So I can put in a commercial plug here. Cambridge actually puts in the contract that we can have them online and give them away, because myself and several co-authors have done that for years and wanted to keep making them available in that fashion. And if the book's cheap enough, then I think most people will prefer to have something, they can read in the bathtub rather than downloading hundreds of pages. The other books that are online are mostly out of print and are basically the deal. If I ever revise them, then we'd have to negotiate, but I can have them up there. And partially because I spent the last year thinking about a lot of this stuff. There are a couple of the books, especially from Springer, one on information or entropy and information theory, that I probably will try and revise along the lines that I've learned. And what will probably happen is there will be a version frozen on the web with corrections and then a second edition, which they'll actually sell after that. So all the old stuff. The only thing that's not really up there is the book with Gershow, because happily people are still buying the hard copy, although it's horribly out of date. So thanks. Okay, well, thank you again.